So, hello students. So, I think you have received all my lectures and you have followed all the lectures. So, just consider my last lectures. So, there actually we had a long discussion about a special case called carbon nanotube. So, what happened? Let me refresh our whole process. We are trying to find out the EK diagram of any material. Okay. Now, what is the significance of finding EK diagram, that we know, because if you have a EK diagram, you can do lot of things, because especially during first semester we get to know that how to handle EK diagram. We can find out velocity called group velocity, we can find effective mass and other parameters also. We can find out current. So like if you have a piece of semiconductor, if you apply some voltage across this piece of semiconductor, what is the current through the semiconductor? So we can eventually calculate it. Now it looks like that finding the EK diagram is very essential and it's very tough job also. Now if it is a three-dimensional crystal like silicon, gallium arsenide, germanium, all these materials, you finding EK diagram is not difficult. Only thing is that we have to consider multiple codes. Maybe we may need to consider multiple basis function, and if the basis function are increasing, so we just observe last couple of lectures, that if you increase basis function, your number of bands also increase, the lines also. Okay, so there are something that we need to discuss here, very important, called subband. So uh, we need to very conscious about what is called bands and subbands, and what is the source of subbands. It's very important. Another thing which is very important these days is like ballistic conductor. You know, if you have a conductor very small, like a 15 nanometer technology, you can understand maybe 100 or maybe 150 atoms are there. It's very small. Now, if you apply voltage across it, and if you want to measure the current, um, you can consider this situation as a ballistic. So, what is ballistic? Ballistic means you have a small conductor. You have applied to voltage and current flowing without, or electron is flowing from one point to another point without having any disturbance. They are not suffering any scattering at all. It's just like a ballistic, just a bullet shooting from one point to another point. Right? So that's called the ballistic, and you understand, if it is a small number of my like my conductor, the probability of having ballistic conductor is high. Now, why we are starting this special conductor? Is it enough that whatever the current expression we have, can it not tackle this thing? Yes, obviously it can tackle. There's nothing else. But people also thinks about thoughts about that, how to make it easy. If you know it is a ballistic conductor, very close to ballistic conductor, so we can simplify few things. Okay. Then getting expression is very easy. Getting a quantitative analysis is very good, very easy. That is the approach. And if you try to read different papers, different journals or whatever, they also impose that scientists also introduce few terms which we need to know. Remember, this is the age people are this is very crucial age, crucial time that we are actually passing through, because people already reach 15 nanometer technology. Now, what is further, people, we don't have any idea. Now people are exploring different materials. Now the question is, if the unknown material comes, and if we don't have this background, whatever we have studied in the second semester, is very difficult to guess. So this semester, what I can see, or this age, whatever the age we are passing through, it's more like it's a material age. People are more concentrated of evolving in new material, then studying the different properties of new materials and try to get a theoretical analogy on this material or theoretical background. Try to develop theoretical background on it. It's very, very important rather than uh, if you have something and how to build, if you have that materials and if you have a transistor out of this material, how to build a circuit and all these things. That is very important, but this stage people are happy to work with our old technology, 22 or 15 nanometer, but half of our scientists or groups are really searching a new material which can further uh, overcome the limitation of your 15 nanometer technology. You know what is that Moore's law and all these things. My suggestion is that go back and check the new generation technology. There are a lot of articles out there, and you see the people are more trying to find out new materials, and people are also looking like if a new materials come, how to get to know about their properties, right? That's the stage. So here we are actually, I told you that we are going to introduce two three concept. One is ballistic conductor, which we already had a discussion, and another thing is the modes and subbands that we are going to discuss. Okay, so just refer our things like this is my, follow my cursor. So this is my graphene EK diagram, and just remember this is the special case only for graphene. Like if you see, I think you have plotted the EK diagram for graphene and density of states of graphene. You see the EK diagram and density of states more or less same from graphene. That's the only one example till now. Okay. This. Now this is a very special case. So let's go for more or less general case. Like we have a parabolic EK diagram. Like you know now during past semester or this semester also, if you have a series of one-dimensional atoms with a periodic atom, and if you try to, if you calculate the EK diagram out of that, get some sort of parabolic picture. Some sort of. It's not always true, but yeah. So this is the parabolic I consider, and we'll try to analyze impose of concept on this thing, because it's more or less general EK diagram, more or less. And if you know this, how to apply those theories, you can apply those theory here also. Any EK diagram. It's just for reference I have taken it. Huh? Okay. So what is current? Since first semester we are discussing about current. Current is I is equal to Q N V. Charge 1.6 into the 90 coulomb. N is the number of electrons or electron density. P is velocity, maybe group velocity. Okay. Now here we can write the current expression like this. So just for a moment we forget about the general expression. So we go directly this expression like I is equal to Q and V, and then can you write these things? I is equal to Q by L factor of this thing. You see this is the same. Why? Let's look at. You will know that we already had a discussion. Let's see N. So let me, okay, what I show you, I just in color go to red. So what is N? So you see this is my N. Okay. Wow, why it is N? Because at each K value, we'll get, because at each K value we'll get a energy. No? That is EK diagram. EK diagram, energy versus momentum. So at each K value we'll get a energy. Okay. And now what is the probability of occupation of this energy by electron? That is given by F, or Fermi-Dirac statistics. Right? So and if you go for summation on this thing, you will get a total number of electrons. Okay. Now you see we need to have a electron density. N is equal to electron density. Now if it is one dimensional, so suppose my electron is a ballistic transport or any transport. So suppose if it is one dimensional, like if my electron is starting from here and reaching from here, if it is a simple one direction like X direction or whatever, so I just consider this is my length from A point to B point, it is my length, and electron starting from here and reaching there. Okay. So this is my length L, and since we need to find out the density, and since it's one-dimensional movement, so number of electron divided by L. Right? If it is a suppose two-dimensional movement, so number of electron divided by area. If it is a three-dimensional, number of electron divided by volume. Right? So that's what L. Now Vx, so Vx is actually, you know that what we are calling for Vx, so we already knew about it. So this is my Vx, and this is my Q. And L is equal to, N is equal to this one. This is my N. So this is my N, this is my Q, and this is my Vx. So I is equal to Q and Vx. Fantastic. Now, look at that. So this is the very common expression now, what is called Vx, and that we know. How do we know? Because we had studied it first semester. So group velocity 1 by HR d EK. That is, group velocity is proportional to the slope of the curve, EK diagram. Okay. Here actually you need to have some discussion, but it is like we have a EK diagram. It's a positive slope. Just follow my cursor. It is my positive slope and it is my negative slope. So it looks like that. This is my positive slope, right? So that means one current is flowing positive direction. Suppose one current is flowing this direction, and if you consider this is my negative slope, because this is, so one current is flowing other direction. One positive slope current is flowing this direction. That's what I have written into. This is my one current is flowing this direction, another current is flowing this direction. Now, if you at equilibrium, definitely this current, one current is flowing this direction, another current is flowing this direction. If it is a conductor, but EK diagram is at a positive slope and negative slope of EK diagram, so it means like one current is, both current is facing to each other, right? Now, if you know, we had a discussion when we'll have first semester, like if you have a plane of observation, so what is the velocity, number of electron passing through this plane of observation, and number of electron passing to the other side. And at equilibrium, whatever the numbers are passing through the plane of observation exactly equal whatever the number is crossing to the other side, because they are facing to each other, right? Now, during in equilibrium, what happens? The number of electrons which are crossing from this side to this side, and number of electrons which are crossing from coming from this side to this side, is actually little bit different. That's what, if you subtract the contribution from each other, from different component, you will get the net current, right? That we had a discussion, right? So here, this current, whatever you are getting, it is actually total current. So I just want to know what is the individual component means. I just would like to know what is the contribution of individual component. It means I have to go Vx by 2. Remember, what the best optimization we may have, the number of electron passing through the plane of observation of pure, if it is my point of observation, okay, with a velocity Vx by 2, and another electron is passing through this plane of its opposite direction Vx by 2. So that is why at equilibrium, the current component from this side to this side and current component from this time to this time is 0, right? At equilibrium, right? So that is why here actually, that's what I written, individual current components. Individual current component is Vx by 2. Well, it will clear in a minute. We'll have a more discussion on it when I'll show you one curve. So, right. And then here it's actually peculiar things. So if you are not comfortable, you can write only Vx, no issue. But I think you should be comfortable, because we had a multiple discussion to find out transport expression, especially the mobility expression, Q tau square by n, and then diffusion component. that time we have discussed like number of electron crossing plane of observation from one direction is exactly equal to the number of electron coming from other direction, and at equilibrium if they are equal then you will get a zero current. Right? You know that part. Okay, fine. So now this is fine, current expression, but people, a scientist thought about, okay, let's introduce another term which would be very handful, and that's called the modes. And just like that I expression, I is equal to Q by L F0 epsilon K Vx, it may be same, like exactly same. But here the difference you see, you have a Fe, it is just like a density of state. Like see, density of state, so like a density of state, multiply the Fermi-Dirac statistic is like this. But they have instead of density of state, because they have to find out the current, they have introduced another component called the modes. And modes is a number. That is the beauty of this. It's a number. It's not integrable. It's a number. Right? So this is actually number. So now the people are thinking like, so this is my general expression, this is also my expression. That's what I know. I is equal to Q by H ME FED. Now if we try to equate it, this current and this current, then what is the value of, sorry, I think I should go for, then what is the value of this one? So if you try to equate it, both the current, so one current, so this is the current I is equal to Q by L, summation this one, and another current this one. It is just like their observation. So because observation is similar, like you have a density of state multiplied by Fermi-Dirac statistics, you will get a number of electrons. Okay, if you multiply it by with Q, you will get a charge. Okay, and now you need to find out current, so that means it should be function of some time and all these things. So number of charge per unit I will get some time. So they are very close to each other, and they try to, all the necessary components should be adopted by this component called ME, and that they are calling it as a modes. Okay, and they try to equate this expression and try to see what is the value of ME. And if you do this and Fe number of modes, and if you do correctly, you will get this expression, del E minus epsilon K H bar Vx by L. So this is your homework. Actually, you can try it. It's very easy. Isn't it easy? It's very easy. Why? Because number of electron, you can find out density of states. This is also density of states. So this is my general expression. You can also equate it with the density of states multiplied by Fe. Correct? So what is my density of state? So density of states is actually del E minus epsilon by K. So if you equate it, you will get it. So what you have to do, you have to rewrite this expression into another form, which is a function of density of state. So you have to rewrite this expression into another form, which is a function of, sorry, this is very difficult, I guess, which is a function of density of states and Fermi-Dirac statistics. So dE, density of states, if you write it, this expression with the density of states, you will get all this expression nicely. Okay. Remember, this is my N. N is equal to what? N is equal to density of states multiplied by Fermi-Dirac. So you see this Fermi-Dirac and Fermi-Dirac gets cancelled. So ME will be left over, and if you can equate nicely, you will get it. Or whatever way, it is, it's up to you. Just put your concept and you will get it. So this could be this you have to solve it. But if you do nicely, you will get this modes, which is number of modes, and it is a number. Okay, this is the part. So summation of delta function pi H bar Vx by L. Right? Just do it. Okay, fine. Now, so this is your homework to find out number of modes, and I can see that this expression is correct. Only thing you have to evaluate, you have to do use your pen and pencil and get this answer. Now, so you get number of modes. So let's let's take this example and try to find out the current. As I told you, I have to explain it. So this is a suppose ballistic conductor. So ballistic conductor, and this is this part. Sorry. So this is my ballistic conductor, and this F1E and F2P is a contact, two contact. You know, just a small ballistic conductor means small conductor, and if you have a two contact, correct? And how to write it? So you need to write like you have a EK diagram, okay? And since you have a two contacts, you have a, you know that part, Fermi-Dirac possibility of these two parts. Okay? And since it is equilibrium, because let's do it for equilibrium. So suppose you have a 4 number of electrons in the left side, that is red colored, and 4 number of is electron to the other. I think it is what, violet colored, maybe. Okay. Okay, other color, and maybe violet color. So 4 and 4 say 8 electrons, but both are actually equilibrium. So, and what you are expecting, if you don't apply any voltage, you should not get any current, because current is totally different. Why? Current, as I told you, you have a plane of observation, number of electrons crossing this plane of observation, and number of electrons crossing from other side. If both are actually equal, then you won't get current, because the current from this side and current from this side are magnitude wise, both are equal, you won't get current. If there is a little bit mixture, suppose 100 number of electrons coming from this side and 100 number of electrons coming from other side, and they are in that, they are facing to each other, you won't get any current. It's equilibrium, so this side minus this side, it will be 0. But suppose 100 number of electrons coming from this side, and here actually 95 number of electrons coming from other side, you will get a current. 100 minus 95, so you will get corresponding current corresponding to 5 electrons. So this concept is here. Like now you see that there is a positive slope. This is my positive slope, as I told you, right? This is my positive slope of current. So what will happen? So my positive slope. So if this is my positive slope, so the current going from just follow my cursor from this side to this side. So positive. It's up to you. And if you think about current going from this side to this side, so definitely negative side will be other way. So it's up to you, because I am considering at the moment magnitude. So let's consider the positive side. So this is my positive axis, okay? Because the slope is positive, so let's look at my current is flowing from F1 minus F2. Huh? So this is my current. So you see, so current from this side to this side, and what is the component from this side? So this side. Again, the current from, so you just extend up to this level, you just touch it. So current from here to here, it looks like this one. And what is the current from F2 to F1? Other way. Okay, but since F1 and F2 in the same energy level, so you won't get any current, right? So that is individual component. If you see I, Q, H, M, E, I put modes F1E minus F2E. So F1E minus F2E, if you see like nicely, you will see that it is giving F1 minus F2. Actually, you are subtracting. Both the current component you are subtracting. And here the number of electrons, because 1, 2, 3, 4, the current due to the 4 electrons is the same from this slope and this slope. So that's what you are getting 0 current. Now let's see the other way. See, like you apply, so this is your condition, suppose, okay, and then you apply some voltage on it. The moment you apply some voltage, so this is another condition, you have a same thing, but here you apply voltage. So you have applied electric field. Voltage means a positive to negative relation. So if it is a positive, it will pull down curve. Now if it is a positive, what is the effect over here in the EK diagram? If it is a positive, more and more electron will everything 4, 5, 6, everything 4, 5, 6. Actually, sorry, there's a small thing I have to add, because we are discussing 8 number of electrons, so you should have a 8 number of electrons also here, right? Because you know, you should not be confused. Again, you just see what we are discussing. So what we have done, we have applied voltage. Once we apply the voltage, so this electric field positive to negative. If it is a positive, what will happen? More and more electron will go towards the positive. Now you see this arm. Initially you have a 4 electrons. Now since due to the positive bias, positive part, so more and more electron will go other side, right? This portion creates some vacancy over here. Correct? Right. So total 8, you have 8 number of electrons, only the placement has changed. 1, 2, 3, 4, 5, 6, 7, 8. So total 8, but since it's a positive you get. And you have to have a positive cool down. So you have a positive, you have cool down. Right? Now, we need to find out the current component. What is the positive current component? You see the positive current component which is coming from F1 to F2. Correct? So this is my positive current component. So that means this is triggered from here to here. Look at that, it is appearing simultaneously. So positive current component which is coming from F1 to F2, F1 to F2, that means at EK diagram it is coming from here to here, right? So it appearing the same. So this is my F2 current, okay? And what is actually the other side current? Correct. Right? So you have, so because you know that F1 try to fill up, F2 try to empty, all these things are there. Correct? So this part, and you have a current because of this gap, because of the number of electrons exist. That means you have a current because of 1, 2, 3. This 3 number of electrons. Remember, you have a current because of 1, 2, 3. This number of electrons. Whatever is exists between this window, and what is the magnitude of this window? QV, because whatever the amount of voltage you have applied, the field voltage across the field or field across the voltage. So that is that, and you will be getting current because of 1, 2, 3 electron, or whatever the amount of electron exists in between that window. Okay. So this is my current expression, but now what we can write? So F1 minus F2 should be QB. Correct? All these things. So ME you put, and you see that you can, and conductance is equal to I is equal to V, because this is QB, and this integration is actually evolving between this limit of E1 minus E2, right? Between these two, correct? So you will get a I by V, that is conductance in this manner, correct? Just so this is the fact that, and we have done these things several times, so don't worry about that, correct? So that means whatever voltage you have applied, you have opened the window of Q by V, QV, and that is actually between the F1 minus F2, correct? So what is my conductance? Conductance is I is equal to V, Q square H M. And this is very important result, because what is the conductance of a small material? At least 10 years or 15 years back, it was very difficult. Not 10 years, 17. So around 2000. So around 30 years back, 30 or 40 years back, there was a lot of debate on it. But there was a nice experiment, and the people have found out that the conductance or resistance of a small conductance is you can derive by this expression, G is equal to Q square by ME, and this is the actually very general formula for if you have a small amount of small material and or ballistic conductor, whatever, it's a small conductor, the conductance of this material is equal to Q square by ME, Q square into ME. Correct? Okay, fine. So you understand, and it is true that this whatever I'm trying to tell you, this is true only for the ballistic constant. Okay. Now the question is, why, as I told you, why we want to go for suddenly so much expression? Like we already had an expression, no? We already had an expression of current, and you see this is my current expression, I is equal to QH bar, density of states, gamma 1, gamma 2, gamma 1 plus gamma 2, F1E. We already at this expression. Now, why we want to go for the very specific expression for another conductor, another material? Why not you apply these things? As I told you, absolutely okay. You can apply this formula also because no harm. But thing is that if you know it is a ballistic conductor, like if you know it's a 15 nanometer technology, or it is down to very, very short, you can actually think about, or very quickly you can think that such a small dimension material should obey a very close to ideal ballistic conductor. Then you can getting a current expression and all these things analytical is very easy. You don't need a numerical solution because if you want to solve this thing, you need to have a numerical solution. It's a function of potential and all these things, potential and all these things. But if you know it's a ballistic, almost on paper you can write all this expression nicely. Okay, so that is what we are doing. Okay, so this is the thing that what we are doing. So you see that. You see, this is my F1 minus F2. So this is my ballistic conductor. And what is gamma 1, gamma 2? That what is the relation? How fast my electron can get into my conductor, or that is gamma 1, and how fast my electron get out from the conductor is gamma 2. That's the gamma 1, gamma 2. What is the dimension of gamma 1, gamma 2? Just refer my last discussion. I think we had a discussion. I think. First few lectures, and after first few lectures we had a discussion on the gamma 1, gamma 2 for ballistic, the expression of gamma 1 and gamma 2 for ballistic transport. Okay, you can find out, or will come out here also in a minute. Okay, now at the moment here actually the ballistic constant, that here actually I am saying, because as I told you that, or you might have observed that during past semester we have studied like called that Schottky contact, or the metal semiconductor contact, right? That also creates a barrier, and that also sometimes opposes the electron flow. That means this gamma, the electron, how easily the electron can get in, it may not be that smoothly. Because if you have a bad contact, you have a lot of barrier height, you may not. Same thing, it may not be so easy that electron can get out if you have a bad contact. But here at this example, I just assume I have a very nice ohmic contact. I have a nice contact. Okay. That means, okay. So now the current due to the ballistic transport. So general expression, what is my current due to ballistic transport? So as we just now have read QH, ME, F1, F2, D. And what is ME? We have calculated delta function pi h by Vs. Now we just, as simple rule, we have a general expression, we have the current due to the ballistic transport. Let's find out what is the relation between these things. So this, if you try to equate those, both are current expression, and we just, for simplicity, I have assumed that gamma 1 and gamma 2 is more or less same, because it's the same material. When you have a metal semiconductor contact, so if you assume that if it is a piece of silicon, you have both aluminum contact. So that we expect that more or less gamma 1 and gamma 2 for both the cases is same. Correct? You have a material and you have same material, you have same metal, if you deposit, you will have more or less same gamma 1 and gamma 2. So at the assumption that we have assume the gamma and gamma 2, and then you know, if you equate it, you get ME is equal to D gamma by 2. So here it's equal to gamma 1 is equal to gamma 2 is equal to gamma. So this ME is equal to DE gamma. This is the density of state. Correct? Fine. Fine. Now another thing, just here, look at this expression. Number of modes is equal to summation of delta function, whatever, pi h by Vxl, and density of states is also summation of E minus epsilon k. That we know. That means this whole thing we can replace it by, means this whole thing we can replace it. This whole thing, okay, it is nothing but, correct, friend? So that means ME is equal to density of state d pi h bar Vxl. That is what I am saying. Okay, so ME is equal to d pi h bar Vxl. Correct? Now, if you try to, now you have a ME, you got just ME expression that modes DE gamma by 2, and just now we got another expression ME DE by pi h bar Vx by L. So both the expressions should be same. The ME expression from here and ME expression for same. Now what is the condition for which both the expression is same? It is very easy. You have to equate those ME term and then you will get gamma is equal to h bar Vx by L. That is actually dimension. And it is dimension, it is correct. Why? Vx is the velocity, velocity by distance. What is that? S is equal to Vt. So 1 by t, right? So that means h bar by v, and h bar dimension is actually joule per second, correct? So it is a dimension of joule per second, correct? Correct. So it is actually gamma by h bar. Yeah. So the dimension wise it is also correct, because Vx by L it is actually dimension of time and h bar by time. So you will get the same, h is equal to joule second. So you will get the same dimension what gamma is actually. Okay, fine. So this actually we get we have a two expression and here you can find what is my gamma, the dimension or how it looks, h bar Vx by L. That means for a ballistic conductor, if you know the velocity or what is called the group velocity, and if you know the length, you will find out what is my gamma, which is very, very important to drive the current expression, right? Current expression, sometimes we know that we don't know what is gamma. But here you can, for a ballistic, like if it is smaller dimension, you can somehow guess what is my gamma. And the gamma is actually group velocity. And how to find out group velocity? It's easy. Because you know Euclid diagram, you know what is group velocity, and you can put it over there. You know the dimensions, you will get to know what is my gamma. The unknown, what was actually not known, now you can, if it is a small dimension material, you can get to know. Fine. So here actually we are going to discuss something. 1 minute. Yeah. So another thing, important part that we are going to discuss is called the subbands. Subbands. Sometime long back, I think one of my students, maybe you have asked what is called the subbands, and I told them not to discuss this topics, because when we are going to discuss about the band diagram, we'll take up. So what is subbands? Let's see. Here the concept I am discussing. So once it is clear what is subband, so you can extend it to the 3D material, 2D material. Oh, that is. So EK diagram with this form of 2D. So this is, suppose you have a EK diagram, and you see this is my EK diagram, because this is the same EK diagram that we have considered here. No, so let's this is the same. Sorry. This is the EK diagram. So let's call parabolic EK diagram. So we are considering this EC. So forget, this is my EC. This is plus EC, and over that EC that parabol start. So this point is EC. Please remember this point. So let me what should be the color? So this color is nothing but EC. Correct? And over there is parabol expression. Okay, fine. Now, so we have that parabola expression, and now let us consider it is actually two-dimensional material. Okay, so what is that? So if it is a two-dimensional material, you know, EC comes EC. So 1 minute. So EC actually, this EC is coming. So H dagger is 2m, and if it is a two-dimensional material, so we have a two type of K, Kx and Ky. We had a multiple discussion of carbon nanotube, graphene, and all these things. So you know, this is the general EK diagram. You can plot. Now, here I'm just giving you one example. Suppose my current is flowing x direction. So this is my x direction. My current. So if it is a two-dimensional material, you know, some current is flowing my x direction. Okay. and this is my kx. So my kx. So just for example, let us draw something. I don't know whether you have a free 1 minute. I'd like to have a free thing is not there. So you have it. So kx. So okay, let us draw actually. Not go for it. So this is kx. This is kx and qi. No? Now what we have assumed that my current is flowing kx and qi direction is quantized. Just like we had a discussion of graphene that suppose kx is my current is flowing my kx and qi is quantized. So what will happen? So if you have a graphene is a roll sheet and if you is a plane sheet, if you roll it out, that means a W. So this portion is actually W direction is actually quantized. For L direction, the current is flowing nicely. Okay, that is what we have. Right. So what is idea? Idea is since k is y direction is quantized, so each of ky value we have to plot ek diagram of kx. Right. So since ky is actually is a discrete value, so each of ky value we have to plot ek diagram. So you know echo diagram parabola, each ky value you have to plot a ek diagram. You have a ky value, suppose one value, and at that value you plot one ek diagram. You go another ky value, another ek diagram. You go another ky value, you will get another ek diagram. Right? So this is the idea. So I have to 1 minute. So this is the idea. So that we have actually done it. So here, since my current is flowing, as I told you, my current is flowing x direction smoothly. So my y level is quantized. So quantized means it has a discrete value. So let's look at n. N is this integer number which dealing that discrete value, and it is like a ky is equal to 2 pi w by n. Because y direction w, okay. And since w is very small, w is very small, and n is actually integer. Okay, and every n value of ky direction, that each and every ky allowed value, you have to plot kx value. Okay, so you will get. So like n is equal to 1, you will get ek diagram of what? N is equal to 2, you will get ek diagram 3. N is equal to 3, you will get so multiple ek diagram. So earlier what happened? We are getting kx and ky, so you will get only one ek diagram. If you have a one dimensional like ek, we get only one parabolic. Since we are actually calculating ek diagram of multiple of n integers, so we have that many of ek diagrams. So n is equal to 2, 3, 4, 5, 6. So that this is nothing but a subband. So what is subbands? So here actually I have told you that okay, so my current is flowing x direction, my y direction is quantized. Even it is not quantized, my current may not be quantized in that direction also. Okay, so even so at ky value, if you have a ky value and if you just fixed one of the ky value and plot kx, though it is not quantized. Here actually special case I have considered it is a quantized. Even suppose both kx and ky are not quantized. So what we can do, that you may have a ky of particular value and plot ek diagram. But the very common way to have a subband, when one direction is quantized, another direction the current is flowing. So you just consider one level of quantized, plot ek diagram. Second level of quantization, plot another ek diagram. Third level of quantization, plot another ek diagram. So this is very common way to plot ek diagram in quantized level. That is very popular method. I saw there are some subband people are calculating where both are kx and qi are not at all optimized or not at all quantized. Still, they took one qi value of n and they plot EK diagram. But I feel that is wrong, because if they are not optimized, so same EK diagram gives you brilliant, you will get all the answer. So all the solution is between the brilliant zone, so it's no need. But still people have done it, which I thought it's not correct. So here actually good thing is that, so I request you, or maybe you do some literature surveys. So thing is that if one direction is quantized, we will consider one quantized level and plot EK diagram in other level. This is the thing. Now the question is, if somebody asks you how many modes are there, it is fine. I have multiple subbands. Now, can you calculate how many modes are there? Yes, we can calculate. It's very easy to calculate. So, this is my modes, density of states, pi h bar Vx by L. So, del E minus it's the density of state. Now, suppose my current is flowing x directions. You know how to calculate the density of states, so, or integration of density of states, since it is flowing x direction, so dkx 2 by L of these things. And what is the integration level? So minus infinity to plus infinity. They just take 2. Now pi h bar by L, and what is the Vx value? You know what is the group velocity? 1 by h bar d by dk. That is slope of this part. That you put. And here, so limit you change minus infinity to plus infinity, instead of write 2 into 0 to infinity. Fine. Correct? And then you calculate it and you will get this one. So this is very, so what is the answer of this integration? 1. What does it mean? It means, this is the meaning. Meaning is, so you have, so this is my delta function. So, so this is my delta function. So it is telling that, if my energy level, so this is my delta function, and this is my energy level. It is telling that this expression is 1, this value is 1, as long as my integral is within this range. Let's color it different. If my integral which covers this range, if I try to so then only you will get a 1 value. If you try to integrate out of this position of this energy, my delta function, you will get a 0 answer. You will get a 1 answer if you try to integrate into 1. So you have to be very careful to put the boundary condition. If you put a boundary condition from here to here, you will get 1 value. But if you try to put a boundary condition from here to here, means, if you try to put a boundary condition from here to here, you see this integral is 0 because my delta function is here and you are trying to put a boundary condition here, so definitely this is 0, right? Now, so that means it has to cover my energy, the delta function, the original of energy, origin of energy. So you have a energy versus kx, okay? Now what is the mode? So you have these things, so you cannot have a, so okay, fine. You cannot have, so if you try to, since it's a delta function, you know it is a delta function, so this portion is 0, no? Because if you try to put a limit from here to here, it won't be 0. So you will get a answer 1 once you go up of this red line, then only you will get 1. So this is the line. Correct? Fine. Now you put another, suppose you have another level, n is equal to 2. So what will happen? So you are doing integration, suppose from, okay, you are doing integration Okay, so what would be the color, best color? Okay, you are doing integration from here to here, so that means you are covering. So you are covering two energy level. So that means one energy levels you will get this one. So if second energy level you are covering more, so that means you will get more. You will get more, correct? So this won't extend more because it covers two number of energy levels. So if you want to cover third, the green one, so it will go 1, 2, 3 more, right? So like what is ultimately, so that means ultimate thing is that you have ultimate thing is that, so overall expression, overall curve is that this is your number of, right? So here I just one thing that I would like to tell, suppose, yeah, so you go back and just one thing that I would like to mention here. Okay, so suppose here, so eraser is there, so let me okay, and in color let me take this one also. Suppose you have an energy level this one, sorry, suppose so you have, this is my energy level, suppose it is epsilon value, epsilon, suppose epsilon 1, some energy level or point, and at this energy point, suppose somebody asks, at this energy point, suppose somebody asks how many modes are there. It is very easy to calculate. It means you look at that, this is a delta function. Delta function means if if you cover the number of energy states, if you cover the number of energy states, you will get the answer 1, right? It means like you have covered 1, 2, 3 number of energy states, and this is the value where I want to know at this energy value what is the number of states and number of modes. So this is, since it covers 3 number of EK value, red, whatever, blue and green, so definitely, so it covers 3 number of EK diagrams, so number of modes, which is a number, that is the beauty, so number of mode is 3. You understand? Suppose you have another, just for example, suppose you have, which will be correct. Suppose you have another EK diagram which is n is equal to 4, right? But my EK, my energy is passing through, my energy is passing 1, 2, 3. It is not passing through this EK diagram, through this EK diagram. So I should not consider this thing. So this is my number of modes. So that means if you have a EK diagram, and if you know which point you are operating, that is delta function. So you have to count the number. So, and now if you know the number of modes, then what is the conductivity of a small conductor? What is the small conductor conductivity? Q square by H into number of modes. Q is constant, H is constant, number of modes, you know, if you know the EK diagram. You get the answer quickly, without doing any kind of expression. And if you know the conductivity, what is the current? If you multiply I by V is equal to conductivity. If you multiply with the voltage, you will get a current directly without doing anything. without doing much integration or much lot of calculation, numerical values, potential, all this. So if you know the numbers, you directly calculate current, and this is the beauty of ballistic. It's valid only the ballistic. Okay. Now this is the homework that I am giving. If you know this part, that number of modes. So now am I asking what is the density of states? This is my EK diagram. Sorry, this is my EK diagram. Now I'm asking you what is the density of states. So this is your this is your homework, and please redo. Please submit the homework. Very important that you please calculate the that density of states. So you know that this is my. So what you have to do? I'll tell you what. No, it's fine. Let you decide. Other than that, I decide. Okay, fine. This is your homework. I have already shared the homework up to 4 or 5. Now please add this homework and please submit it. Okay. Thank you.